So let's see now the steps that we will need to do in order to perform the principal component analysis. So the first step is to normalize the data. So this means we need to center our data around the origin. So for example, we have data like this. So we have data x2 versus x1. We see it's this cloud of points that we have like that. And in order to make the algorithm work properly, we need that this data is centered around the origin. So in graphical representation, it means that we need to do this. We will shift the data in such a way that the mean value of our set in both axes is 0. So the way how we will do it is that we will take our set, we will calculate the mean value in the x2 direction and x1 direction, and then we will subtract this mean value from all our samples. So this will shift the data like that, where we still have the same data, but now it's centered around the origin. Well, not same data, but graphically the same data. It looks the same, but now it's centered around the origin. So we will do this in an arbitrary number of dimensions. So this is shown here only in 2 dimensions, but we can do it for n dimensions without any problem. And the next step will be to find out the direction of our principal components. So here we can see how they will be oriented. The one principal component will be in the direction of the maximum variance, so like that. This will be PC1. And PC2 needs to be perpendicular, and it will be in the direction of, let's say, second maximum variance. So the second step will be to find out what is the variance of our data and the covariance of our data. So we will work with a covariance matrix. So let's say, for example, we have a case of 2-dimensional data. So the covariance matrix will be 2 by 2. On the diagonal of our matrix, we will have the variance. So here this will be variance in the first direction, and this will be the variance in the second direction. And the covariance here will tell us what is the mutual dependence between signal 1 and 2. And here we'll have the mutual dependence between 2 and 1. But we are assuming that this is symmetrical. So here this will be the same number. So here we'll have covariance between 1 and 2, and this will give us the same number over here. We know that we can calculate the variance based on this equation like that. So we will take the average value minus our sample, and we'll use this formula for calculating the variance. But since we have normalized the data, it means that our mean value x bar here is 0. So we can take, this will be 0, and we can take directly this sum of xi squares. And that's what we can see over here. And the reason why we have done this is that this allows us to transfer our problem into a matrix calculation. So we can of course calculate a variance like that. We can take our samples x1, x2 and so on. We can just sum it together, and this will give us the variance. But if we want to speed our calculation and make it universal for n dimensions, we will need to operate with vectors and matrices. And you can see here what we are doing. We have x1 squared, x2 squared, and so on, and we're summing all this. So if we represent this in a vector, we can create a vector which will be x1, x2, x3, xn. And now I want to calculate the square. So I will multiply it with this same vector, but if I want to multiply x1 by x1, x2 by x2, then this vector needs to, the first vector will be transposed. So in a mathematical representation, it's looking like that. I will take my vector x, I will multiply it by x transposed, and I will divide it by n. And x is nothing else than our input data. So I will take my input data like that. I will simply create a transposed version of my vector, and I will calculate the the variance of my data. So what we are doing graphically is this. Here in red we have the original data. That's arbitrary data, so it's not centered. Now after we have centered the data, it's around the origin. So here we have 0 and 0 mean value in both directions. And we are trying to calculate the variance of our data. So this is the width of our interval in this coordinate and in this coordinate, like that. If you want to calculate this in Matlab, you can use obviously a function that's already available. So we'll create the covariance matrix. We'll see in the Matlab code how this is done. And if, for example, I now want to calculate the standard deviation of my data, I will just use the function for standard deviation. So I will have the covariance matrix like that. We can see here the value for my particular data that I've chosen. So I can see that variance of my signal 1 was 0.6 and variance of signal 2 was 7.8. So this gives me a larger variance and this will give me lower variance. And we can see that here the covariance is obviously the same. So this covariance is telling me what is the mutual dependence between signal 1 and signal 2. Now the third step will be to take this covariance matrix, which is here, and it will be necessary to calculate the eigenvalues and eigenvectors of the covariance matrix. Now what does this mean? Now if we are looking for eigennumbers, then we are solving an equation like this. We are calculating the determinant of our matrix. Now this should be C. There is one reason why I have kept this as A. We are calculating the solution of this equation, and the eigennumbers of the matrix that are fulfilling this equation are, well, the numbers that are fulfilling this equation are called eigennumbers. Now the reason why I have actually kept this matrix A and not C as the covariance matrix is simple. Now you may be familiar with calculating the eigennumbers or eigenvectors of a dynamic system from some control classes, for example. And in the control classes we are using the matrix A to describe the dynamic of our system. So for this reason I have kept this A, but will obviously replace that with C in our calculation. So this solution will give us the eigennumbers, and if we are looking for eigenvectors, then that's a solution of this equation. Now I don't want to go into mathematical reasoning why this is so. I just want to show here the usage, and the usage is super simple. In Matlab you just use this function eigen that will give you the eigenvectors and eigennumbers of your matrix. So here this will be your input matrix, and this will give you your vectors and eigennumbers. So it's simple as this line in Matlab. So now we have the eigenvectors and eigennumbers, and we need to order the eigenvectors by the size of eigennumbers. So let's say that we got those two eigennumbers. So one is 8 point something and the other one is 0.06 approximately. And so this means that we'll first take this one, because this is larger and it will cover, let's say, more energy in our signal, and this is smaller, so it will cover less energy. And here we have our eigenvectors. That's the result of calculating that with this function for my specific data that I have used in this example. So here this is my eigenvector, and this is my eigennumber. So I see that my eigennumber, the largest one, is on the second column and second row. And since Matlab returns the eigenvectors in columns, then it means that I will need to take this one in the second column, like that, as my first eigenvector, and that's this one you can see here. Let me just mark it. So this is the largest that corresponds to that number. So from this number I say I take this eigenvector and I will arrange it as a first column in my result. And this is, let's do it in different color. So for example, green one. So this is my second eigennumber. This in the first column, this corresponds to the first column over here. So this one, and this will correspond to this second column of my result. And you can continue with this with n dimensions. So once you have this working for 2 or 3 dimensions, which we can imagine quite simply, it will work also for n dimensions. And the last step will be to select only some limited number of eigenvectors. So for example, if I would be doing compression of data, I will represent my input data only with this first eigenvector, and this will reduce me the dimension. So what have we done now is that initially we had some input data x, and we now want to represent this with an estimate of x hat, and this is an equation that looks like this. Now our estimate is my original data that is multiplied by this matrix P, which is composed from the main components. In Matlab, you don't need to do all those steps. You can. I will show you a code that is doing that. But since this is a really useful function, the PCA method is covered in Matlab as well, and it's a function that's called, surprisingly, PCA. So you have your x vector with data, and you will just get the outputs that will tell you what are the major components, what is their energy, and so on. So what we've just done is that we have represented our input data x as some estimate plus some error, and this error covers all what was neglected in our calculation. So it covers all the components that we have neglected in the analysis of the problem, that we have eliminated here in this last step. So before we go to the usage in sensors, let's do a demo in Matlab where we can actually see this algorithm with all those steps, and we'll see the results, and we can compare it with this PCA function in Matlab. So as usual, you have the code available in Moodle. It's example 5 principal component analysis, and I will be using a random signal. So I have generated two variables, a variable a and variable b. I didn't want to complicate this problem with multiple dimensions larger than 2. I know that my variables needs to be correlated. So I have generated variable a, and variable b is correlated to a, because here I have just multiplied it with some constant. I have added some constant. In both cases, there will be some random noise on my signal. So this is here something that's generating a random noise, and here we're generating the random noise. My noise, by the way, is with a normal distribution, so it will be Gaussian distribution for my noise. Then I create my vector x. This will be my input data. So if you would analyze some real data from real sensors, you would obviously not generate these signals, like random signals, but you will directly get this input data, and you will arrange this input data in some vector x. Now I'm just plotting something. We can use directly the function of Matlab, here the PCA. I will not do that for the purpose of seeing how this algorithm works. So here you have actually the step-by-step calculation of the data that we are using. So we said that the first step is to normalize the data. So I need to find out what is the mean value of my data. Here I'm using the function mean, and then I need to subtract from all my samples this mean value. So that's what's happening here on those two lines. Calculate the mean and calculate the normalized x by subtracting the mean value from all my data. And then I can see here just the plot. So let's run it like that, and we'll see what is it doing. What is it doing graphically? So here, this red points, that's my original data. We can see that it's centered somewhere around this point probably. So around 10 or 12 on the x1 axis, and around 40, 45 around x2 axis. And the green points are the centered data. So I took the mean value in both axes, I subtracted from all samples this mean values, and this has centered this cloud around the origin. So here around 0, 0, that's where the green cloud is centered. You can see we have kept all those data, but here we have just shifted them. Now I want to show you something a little bit more. If you, well, I don't have, okay, I don't have it in this code. I could show you the transformation, for example, the rotation. So let's see. For example, here I kept it on purpose in the code. I think from mechanics, you know the rotation matrix, which allows you to rotate something by some given angle. And here you can see that we can actually rotate the data. So let me just do that very quickly. So I will just define my rotation matrix so that we see just what will happen in the chart. So I'll just define a new figure. So now note that my data is going like this. It starts at the bottom left and it's going to the top right. And now if I will rotate the data just by simply multiplying the data like that, I can just plot my new data, and we'll see that now it will be rotated. So it will be like this. I have rotated that by 75 degrees. So I can very simply rotate my data, and I can also translate them if I know the rotation matrix. So this is the relation between, let's say, the algorithm that we're discussing and, for example, mechanics. So what I'm doing next is that I have this data which is already normalized, and I will calculate the covariance matrix. In Matlab we have a quite useful function, covariance matrix. I just take my normalized data and that's it. Then step 3 is to calculate the eigenvectors and eigennumbers of my covariance matrix. And again, there is a function AC. And at the very end, step 4 is that I will create my principal components, and I will choose the components that have the largest value of the eigennumber. So here I'm just going in a cycle through the main vectors. Here I have sorted them in descending order, and here I can select what the values that will I have in my representation. And the last step will be to apply this to the original data. So the last step is this one, where I'm trying to represent my original data as some linear combination of the principal components. So let's see what will this do. Just continue this, and this is our outcome. Well, the yellow is not a good color, I see. So let's make it in red, for example. And the result that I want is a chart like that, or a representation like this. I see that now on the x-axis I have a principal component 1. That's the direction of maximum variance. So if I put the two pictures next to each other, then PC1 will be this direction, the direction of maximum variance, and PC2 will be the direction of the second maximum variance, which will be this one in my case. Now you can plot it quite simply for 2 dimensions, but if it's like more dimensions than 3, then it's not possible to visualize it and to plot it. So that's why here I have chosen just the 2 dimensions. Now in my problem here, I have kept all the eigenvectors. So I have kept both vectors I had here like that. So I did not lose any information. I just rearranged the problem so that it gives me the same data, but the inputs are different vectors. Now, why do I need it? Well, the reason is that I can use this to calculate the squared prediction error. And the squared prediction error is a way how we can make an estimate how far, in quote marks, we are from the case where there is no problem in our data. So we will do this as an online calculation when new samples will come in, and we will be looking for how far are we from a flawless estimate. So this means that if I calculate the squared prediction error with some equation that I'll cover in a minute, then I'll get some value for the flawless data that I will say now everything is correct and this is my correct value of squared prediction error. And if then later there will be some problem, I can say that this value of squared prediction error will be larger than something, some threshold, and I will say that there is an error in the data. And in order to do this, I will need the principal components. So I will now take my principal components, and I will use this to calculate the square prediction error. And you can see the equation over here. So x and xt, that's my data, and this is my principal components. So what I'm doing is that I have defined some error, and now I'm calculating the square of my error. Why square? Because I don't care if my value is positive or negative compared to my correct signal, or to my estimate, but I care about the distance. So I don't care if it's above or below, but I just care above the distance. So that's why here we are doing this x squared. So we will be calculating this. We'll take our original data. This is the data that I have obtained from my problem, and this is my estimate here. This is well, this times this is nothing else than this is my estimate. So I'm basically multiplying my estimate here with my original data, which is here, and I'm looking for how far this is from some threshold. So let's see a demo in Matlab. I have made a demo that is quite similar to one of the examples. It represents different temperatures. I have chosen like 6 temperature readings, and I have data like this. So every time I have a constant data plus some noise. So this is sensor number 1. It has an average value of approximately here, so let's say 580, 560 probably. And here I have the variance. So this is the noise that's coming from measurements from the transfer signal and so on. Signal T2, temperature T2 is here. You can see it has smaller variance, a little bit lower value, T6 and so on. And at some time from sample 1500 here, I have introduced an error in sensor number 5. So until this time, like from 0 to 1500 samples, this was okay. And I will use this to find out the value of my threshold. And after this, you see that the value now is drifting. So this could represent, for example, a mechanical problem or some electronics problem in the sensor. And we will calculate the squared prediction error based on this equation, because we already have the main components, so we can just multiply that by our signal, and we will see if we can see on the threshold this reaction. So in other words, if we are able to detect the problem over here. So let me now switch to Matlab. Again, this code you have it on Moodle. Example 6, PCA sensor DAC, and it's using simulated signals. So here I'm generating random signals. You can see that they have this is the value, this is the, let's say, DC value of my signal. So the first signal will have mean value of 550, this one have 550, and so on. And I'm adding some random noise, so random normally distributed noise with this mean value. You can play later with this value. And here I'm adding the error in my signal, T5. So I'm taking everything from sample 1 to 1500 as is, and then I'm introducing some error after this sample. And then I have created the vector x from this data. Now if this would be a real data from real sensors, you would get this x directly from your inputs, and you would not need this signal definition. Then I'm simply plotting the signals so that you can see it. Here I'm using both approaches. I'm first using the PCA value, the PCA function, so that we can see the outcome of this PCA function. And then I'm running the same algorithm like we've seen a few minutes ago, that is actually doing step by step the same PCA analysis. And at the end, what will I get is that I will be able to find the error in my signal. So let's see that. Now this is my input signal, the original data. We can see that here we have the signals from the sensors with noise, and here something started to happen. We know that we need to normalize the data in order to make the algorithm work. So this is how the normalized data looks like. So we can see it's all centered around 0, and now plus some noise. And if I calculate the squared prediction error, I will see this. So here I know from my assumption that I have made on the beginning, that until sample 1500 everything is okay. So I can see what is the value of my squared prediction error. So it should be something like this, so smaller than, for example, this value. And this allows me to set a threshold. So I have set the threshold, I think it was 8 here, 8 to the power of 5. So I have set the threshold to be over here. And if my signal is below the threshold, I will indicate no fault. And if my signal is above the threshold, I will indicate a fault on my output. And of course here this is not perfect still. Here we can see the noise. That's because I have set a fixed threshold. And in a real application, you would probably need something like a hysteresis, so that you don't have this oscillation when it's jumping back and forth. So let's see how this is done in Matlab. So this is the algorithm for the PCA, and the fault analysis is actually this cycle at the very end. I took the original vector of my data. I have multiplied that by, well, this is nothing else than the equation that we see over here. So xt is my original data transposed. So that's this one. Then it's multiplied by the eigenvector, which is all ones, minus this is the result that I got from the PCA with the reduced feature vector, and this is again my original data. And this allows me to calculate the squared prediction error. Now so far I did not reduce any of the vectors, so I have I have used all my data that I got on the beginning, and that's what you can set actually here. So from the PCA analysis, you will get all your vectors, all your values, basically vectors like this. And then what you can do is you can choose how many vectors you will use. And you typically do this based on the energy, for example, that is covered in this signal. In other words, variance. If there is large variance, there is a large energy. If it's low variance, it will not bring you that much if you get rid of that. So here in this part of the code, you can actually choose the reduced vector size. So in my problem I had 6 variables, but for the reduction I have used only 3 of them. Only the first 3 ones which had the largest variance which, by the way, we can see here. So let's see here the value, not m. I think it was not I. No, let's where is it? Let's see it here in the eigenvectors and the eigennumbers. So it's w and d. So this is the eigennumbers, and we can see what are the values of our eigennumbers, and now we can arrange them based on the value of our eigennumbers. So this is what this part is doing. This is arranging them in the descending order based on the values of the eigenvectors. And we can see if it will make some difference on the analysis if I take all the vectors or if I get rid of some of them. So let's just try to use all of them, which is 6 here. It will not make any difference here. The only difference here is that now we have to set a different value of my threshold, because here you can see that now my value, since I'm using different numbers, here I have a threshold of 6, so I would need to set a different threshold like that. But it will not make any difference for the detection of my error. So you can also see that it has an impact on the calculation speed. So now for all 6 vectors it took longer because I needed to work with a significantly larger number of the dimension of the matrix. So here, if I reduce it back to 3, or then let's try 2, and let's see what will this happen. Basically, we'll have faster analysis, and we can see that now we again would have to set the different value of my threshold. So by using an approach like this, you can quite simply detect the error in your data. You have the algorithms that you can use. As I said, there is a function in Matlab which you can translate in C, for example, and I find that this is a quite useful function, not only for sensor analysis but also for other purposes. Now let me finish. What is the other function where you can use this PCA? Well, one of them is that you can search for patterns in data. So, for example, if I go back to my examples, let's say this chemical one, by using this analysis, you can find out if there is some mutual relation between some components. It means between some data that you get, and between your different inputs. So, for example, in this case, in the case of chemical sensors, they found out that if they plot it like this, PCA2 and PCA1, that here they will be having one chemical, and here they will have a different chemical. So this allows you to, for example, create a sensor or an algorithm that will detect those two chemicals and will distinguish them from each other. The second use is of PCA is, for example, if you want to compress some signals or even some images. And on the next slide I have some links where you can actually see some videos. So the PCA is quite a useful method if you want to reduce the number of data that you are transferring somewhere, and you don't want to lose that much information. The third example is that this allows us to visualize multi-dimensional data. So, for example, let's say we have 100 input variables, but how do we know what is important? How do we visualize it? If, for example, I would like to visualize it again in a chart like this. So if you do this PCA reduction of components, then you can plot this by those coordinates. You can plot PC2, PC1, or you can choose any other components, and in this type of chart you can see, okay, there is a dependence between this component and this component. It looks like cloud like that, and I get a distinguishable region for this input case and for this input case. And this allows you to clearly visualize the, let's say, sensitivity of your sensor, or maybe it will be overlapping. So in this case, you will not be able to tell anything. So maybe it will be something like this. Those yellow points and those magenta points are overlapping. So with this kind of analysis, I cannot distinguish, for example, two concentrations of my chemical. But it might be possible with different methods. So this allows you to tell if you can distinguish something or if not. And the last example where we can use statistics, PCA, is statistics. So it's like a useful statistical method. There are entire courses that you can visit about PCA and statistics. I'll not cover that. And of course there are obviously some other usage as well. So what are the additional materials? If you would like to learn more about it, there is a quite great video tutorial series about PCA from some guy from I think University of Wisconsin, I believe, and he has several videos about that, how to use it. He has some Matlab examples. He's using that for image analysis, so to reduce the number of images. I think he's searching for a dog in a picture and stuff like that. So it's quite useful not only for sensors, but it's useful also for let's say image processing, for example. Then there is an entire book about all those problems, again from one of the same authors, data-driven science. You can download it in this PDF. There is like a really good tutorial class about PCA. So the PCA is not only for sensors, but it's also for many other purposes. So at least I think this should give you an idea that this method exists, and if you will need it, you know where to begin. Okay, that's all.